Hello, in this video we will continue our discussion on the balance of angular momentum or Euler's second law. The balance of angular momentum about the fixed origin O can be written as MO is equal to H dot O, where remember HO is the angular momentum, the moment of the linear momentum, R cross MV. Let's first talk about conservation. When is the angular momentum of a system conserved? Well, what does it mean for the angular momentum of a system to be conserved? Well, this means that the angular momentum of the system is constant, right? HO is equal to a constant. This means that the time derivative of HO, which is the time derivative of a constant, would be 0. H dot O is just equal to 0. So that would mean, or that is true, that is the case if the sum of moments about O is equal to 0. If the sum of moments about O is equal to 0, then HRO is equal to 0 and the angular momentum of the system is conserved. So when MO, the sum of moments about O, is equal to 0. That's our answer. Let us think of an example. A common example where the angular momentum of a system is conserved is in central force problems. Okay, in these problems, for example, consider, let me give you an example of these problems. We have the Earth, say, Earth, and we have some satellite orbiting the Earth. The only force that is acting on the satellite is the gravitational pull that the Earth applies on the satellite, Fg. Now this is a central force problem because the force Fg acting on the satellite is always gonna point towards the center of the Earth, basically, which is the origin of our system. So no matter where the satellite is, the force points towards O. That's what makes this problem a central force problem. So notice in this case, if I want to calculate the sum of moments of the forces acting on the satellite about O, the sum of moments about O acting on the satellite, that's equal to R to the satellite cross just F, which is Fg. And notice that R and Fg are parallel, so MO is just equal to 0. This means that H dot O is equal to 0, then HO is equal to a constant or conserved. Okay, so the angular momentum of this system is conserved. I can calculate the angular momentum of the system then. HO is equal to R cross MV. If I use polar coordinates, then I can say that R is RER and V is R dot ER plus R theta dot E theta. So then the angular momentum of this system would be just M R squared theta dot EZ. Okay, notice very well that HO is going to be constant throughout this motion. We're going to talk about this problem more in the next homework. One last thing that I want to mention is the angular impulse angular momentum equation. That's in direct analogy to the linear impulse linear momentum equation. Remember, the balance of linear momentum is equal F equals G dot, and we can write the linear impulse linear momentum equation as the integral of F dt is equal to G between T1 and T2 is equal to G at T2 minus G at T1. So then we can do the same analogous thing to the balance of angular momentum. So starting with MO is equal to H dot O, I can integrate both sides of this equation with respect to time to get that the integral of MO dt from T1 to T2 is equal to HO at T2 minus HO at T1. So then if the sum of moments of the system is equal to 0, if this term is equal to 0, then HO at T2 is equal to HO at T1 is equal to HO at any time, basically, because the angular momentum of the system about point O would be conserved.